preview. Okay, so this number E, okay, is not a variable, which I just called it by calling it a letter up here. It's a natural base and has a value of about 2.71, and it's something a little bit like pi where I could keep going with all the decimals, but basically it's about this value. And it's called what's called the natural base. Now, for now, we've been using it, and we'll be using it today in this equation to find compound interest, okay? Compounding continuously. However, E is going to have another use in the future, and I'm not going to get real in-depth here, but it's the inverse, or it's the opposite of natural logs, and we're going to be getting into logarithms in the next section. So, for instance, in the past, when we've had like square roots and squares are inverses, okay, or opposites of each other, the same thing that's going to happen here with us coming up is that if you ever have an ln, a natural log, and an e, those end up being inverses and help us be able to solve expressions. Okay. Just wanted to put a little intro in there, and that e has more uses than just when we're doing an interest formula. So, what I'm going to do with you is this first problem here, and then the last three are actually going to be kind of some last-minute things we kind of need to go over with. Interest. So, alright, example. Friend comes to you all excited. Tells you the bank he just visited offered him 4.5% interest compounded continuously for 5 years on his $1,000 savings. He took his money out of another account that was paying 5% compounded quarterly because continuously will make him so much more money. Is he right? Can you show him if he's right or wrong? So, if I'm trying to figure this out, if it's compounded continuously, I'm going to use that PERT equation that's up above. PERT. My principal is 1,000. E is itself, because again, that's a value. And then my rate is the 4.5% as a decimal. Now, does it mention up here at all? Yep, 5 years. Okay. So I'd multiply those two together, my rate and my time. So let's just see out of curiosity how much that is. Now, if you don't remember where E is at, if you hit second and ln, kind of interesting that they chose to use that in the calculator since they're inverses of each other. It already gives me the parenthesis that I need. Turn this into an exponent. Just make sure you don't close it until, oops, I double parenthesis. I don't need two of those. There we go. Oops. Boy, my zero, I'm having all sorts of issues. Okay, that's better. So my 4.5% times the 5 years, and that's my exponent. So I go ahead, I hit enter. I'm like, all right, so $1,252.32. So I'm like, all right. So then I go, and I need to check his other. But now again, the formula won't be the same, because I'm not compounding continuously now, which is the key right here. Now I'm compounding quarterly. So, different formula. Got this. 1 plus my rate quarterly. How often does that happen in a year? 4. So that's my denominator of my fraction here. N times my t. So whatever I divided by here is the same number I use up in the exponent. 5. So now let's see what's up here. And I could have just put 20 here as my exponent, but I just put 4. Rot-row. What did my friend just do? Stupid mistake. Because by taking the money out of the account that was paying a larger percentage and paying it quarterly, he still would have ended up making more money with the quarterly. So it's just kind of one of these things where words or advertising can kind of mess with us. just because you see something continuously or daily rather than, yearly or whatever it happens to be, doesn't mean that it's necessarily going to be better for you. Okay, so it's just kind of the thinking process that does it. So yeah, you just cost yourself about $30 and took the time to do all that. What a do that. For math side. So what your job is going to be to take care of the three on the bottom. And again, the three on the bottom, basically going along with the type of stuff that we've been doing. We're making comparisons between the types we've been using, the simple interest or the compounding after a certain amount versus continuously, to kind of see what, if any, type of difference there's going to be as those are getting situated. So if you want to take a minute or two here, because it probably won't take you very long to knock this out, just get those situated, especially with a couple of examples up above. That's fine, because then, if some of you are flying along here, we'll be just jumping into the quiz preview. We've got plenty of time to be able to get all of this situated. So, let's kind of take a peek here. Let's see what we've got. State whether the functions represent growth or decay, then give the y-intercept and the end behavior. Okay. Now, let's see what we got working here. First things first. Growth or decay? So we should be able to do that without punching it in. Right. Now, how did you know it was growth? Okay, right. If I look at my base, okay, right here, and it's greater than 1, even if it's fractional, if it's greater than 1, usually that's going to be growth unless, what I mentioned before, I see a negative exponent somewhere. That causes a little bit of an issue. So this is going to be growth. Now I should be able to figure out my y-intercept without too much hassle either. What's my y-intercept going to be? Hang on, we'll continue in a second. There's no shift, so I should be able to look at the original expression. 0, 3. And again, when it's an intercept, remember, that's a point. It's not an equation. I really don't want to put y equals 3 because that's the equation of a horizontal line. And that's not what I want. I just want this one point. Now, if there are shifts, that can change. But for the most part, if I don't see a shift, it's moving me left or right. That typically means we're going to be okay here. Now, it does help, I will admit, to be able to take a peek at the graph to be able to figure out some parts of this, even though I still think we could do this without it. But just as a backup plan, make sure we get everything good here. Okay, so we visually see its growth. I visually could look and see the y-intercept. What's my domain? Okay, in which the case on these, that's what your domain is going to be. So actually the easiest question that you see on this. What about my range from bottom to top? 0, it approaches 0 down here at the bottom, and then goes off to infinity. Again, I want the parenthesis because it doesn't hit 0, it just gets really, 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 really close. So we're like, all right. And then end behavior. I don't know why I didn't put one of these in here, but this is again where we get into f of x approaching things, and that when I'm working with these, I need one of my x's to approach negative infinity and one of them to approach positive. Well, that's okay. I'm surprised I didn't have written in here state the end behavior. That's kind of strange. So, remember, when you're looking at this, as x approaches negative infinity, remember, that means as x values are heading to the left, what are happening to my y values? Yeah, they're getting closer and closer as this moves to the left. They're getting closer and closer to 0. So that would be my y approaches 0 as x heads to the left in negative infinity. Then as x heads to the right, what happens to y? It approaches infinity because it starts going up exponentially. So if you always get one of each for the x's with negative and positive infinity right away, hopefully you can kind of read into that looking at the graph. So that's basically what we're doing on these. I'll switch it over a little bit here. We got the same thing going. And again, I'm glad Ben had mentioned it before. When you get a negative exponent working, we talked a little bit about this when we saw it the first time. What actually ends up happening here, so I've got a negative x, and I graph it, you're like, well, wait a minute, 1/2 normally would be decay, but now it looks like it's growth. So what's the deal here? Basically, what's happening is negative exponents cause inverses. So what you're looking at here basically would be the equivalent of you looking at that expression. Well, if it was 2 or 2 over 1, you'd say, oh, it's growth. It's greater than 1. So that's kind of the thought process I'm going through when I see that negative exponent. It's going to make what's inside look like it's reciprocal. So when I do this, now is that going to mess with my y-intercept? Nope, not going to mess with it a bit. It's still at 0, 4. It's 0, my a value. What about my domain and range? Still negative infinity to infinity. The x values will still keep going forever, both to the left and right. And my range? Yeah, it looks a lot like the last one I did. 0 to infinity. Well, if it looks a lot in behavior like the last one did, I wonder if the end behavior is going to act the same way. And it actually is. Your end behavior is going to act exactly like the last one did. Because as x is heading to the left towards negative infinity, it's approaching 0. It's getting closer and closer to the x-axis. As that same graph heads to the right and my x values get greater and greater, so do my y values. So actually, the end behavior ends up being the same as 2. So again, it's just getting some of that base information in there to kind of work with, but it's stuff we've been doing quite a bit too. Any issues with those first couple before we actually get into a little graphing here? Okay. Now, I know what most of you, and what I would probably do as well on this next part. Okay, when you go to graph the function, the only real thing I'm going to need to be careful about here is notice I want the x, okay, to just be my exponent. I can put it this way, and it's not going to be a big deal. If I ever want that value afterwards, like in this case, if this was x minus 2 as my exponent, I'd need parentheses around it. Otherwise, the calculator knows, oh, this is 2/3 to the x, and then I'm going to minus 2. Now again, I want an accurate enough looking graph that I would want you to get some values on here that are going to make this a little bit easier to see. So like here, for instance, like it's -4, okay, it's a little over 3. And I'm just going to take some of these values that are coming up as it starts to approach its lowest point. And again, there was a shift on this one. Now, if I'd have asked a question on this one about what was the shift on this particular graph, what could you tell me? Down to, okay? This is down to, just in case I'd ask that sometime. So that means now my new bottom point, instead of being at 0, would be at 2. So is that going to change my domain at all? No. But what does that do to my range? Think about bottom to top. What's the... It does. Now my range, instead of starting at 0, starts at -2, which I found out from the shift. If I have up or down shifts, that's going to affect my range. So that's something I've got to keep an eye out for. Okay, but only if it's an up or down shift will that happen. So I'm like, all right, but that's still not bad, because I got the calculator to give me all the points, so I should be able to keep that in line. So then I move to the next one, and I start thinking about the shifts again that are going on. This is the type that I was talking about in the first one. I want that x minus 4 to all be part of my exponent. So I have to put it in parentheses for the calculator to know what I'm doing. Yes, ma'am. Okay, if we need to fix a table, if you go to second window to get the table set, you can always, this is what it normally would be. So if you get second table set, it's some big thing. If you always put the start at 0 and the change in table at 1, it should get back to some normalcy for you here. So when I get into my chart here, I kind of start to look, I'm like, okay, now where can I get points again? Well, it looks like I always like to get points that are whole numbers. Those are always nice to get every once in a while. So I just start to plot some of these dots, and I'm going to make sure, like graph, okay, it looks like it's going to approach 0. It comes down in a hurry and then levels off. And again, I don't want to be sloppy and just go straight through the x-axis and be like down here somewhere. Then we're having issues, and I'll probably circle it if it was on the quiz that way. But it does get us back to a more prototypical domain, which just doesn't change. What about the range this time? Okay, back to 0. Because the only time that range is going to move is if I have an up or down shift. What's that -4 signify for a shift on this one? Okay, right 4. Right-left shifts don't mess with my range. Up and down shifts do. And speaking of those shifts, kind of interesting, it leads right into this. Next one, number 5. If f of x is 7 to the x, and g of x is 7 to the x minus 3 plus 2, explain how to obtain g of x from f of x. In other words, what are the shifts? What are the transformations? There's 2 of them. Okay, right 3 from here. So again, that's my left or right shift up in the exponent, and it's the opposite of what I would think, because it's x minus h, so it switches, and then up 2, and that's all you got to say. So nothing too bad there. You're like, all right. So let's see, 6. The amount of isotope, radioactive isotope, decreases 4.5% per year. A sample originated with 245 grams. Determine how many grams of isotope remain after 15 years. Use, and this doesn't mean I use plus and minus. It means you have to pick which one you're going to use. Which one am I going to be used since it decreases? Minus. So when I go to figure this out, y equals my a, my starting point. 1 minus my rate. So the 15 will get me my years. So whether you use the chart for that or whether you just type this one in, if you're only looking for one, how much am I going to have after 15 years? Oh, 100 and something. What? Oh, I'm with you. 122.8 grams. If, okay, and on some of these, if you used the y equals in the chart instead of just plugging this into your calculator, I've said before, you may have a slight rounding difference. That's not something I'm going to jump on you and take off for. I'm going to have done it both ways, so I know for sure which one's which. Okay, that's all we do there. As we head to the back, a city's population is currently 45,600, but it grows at 2.3% each year. Write an equation to represent the city's population, then calculate how many years will pass before the population reaches 60,000. All right. First part isn't bad. One plus my rate. And in this case, I don't know how much time because what I'm going to be doing is plugging this in and then using my table to help me figure out the 60,000. Again, we've got options on things like this. And again, make sure you get that exponent, that caret button in there, because I am known to forget that sometimes. So if you look at it that way, there's a couple of things you can do here. You can go to your table. And again, before, we were talking about how we want to get approximations on things like this. If you were working on a city's population, you're not going to worry about the exact day, okay, because this is just an estimate anyway. So when would that happen again? Okay. Yeah, somewhere between 12 and 13 years. You could, yeah, you're going to need to. And that's a good thing to ask. The question was, when we get to number 8, do you have to make up how much you were starting with? The answer is yes. It says you invest part of your summer income in an account to collect 4% on interest continuously. How long will it take for the account balance to triple? So yes, you would create a number for your P. So let's say, for instance, you decide you're going to make your principal 10. I'm going to do my own this time. Or if you want to do 100, you could. It's all going to be the same no matter what you're doing on these. So your rate, and I don't know how much time. But I'm going to be looking in my case to figure out when my A value becomes 30. Now, if you did 100, it'd be 300. If you did 1,000, it'd be 3,000, whatever that happens to be. So my particular equation, I could put either this, or I could even put when 30, in my case, equals 10e. But if you even just wrote this, that's legit. But again, if you used a different value for your starting value, you would need to use that instead. Say that again. 600. So make sure you get that initial value in. And no matter what, no matter what initial value you started with, you should end up with the same value at the end, the number of years it would take to triple. So, in my case, I'm going to be looking for 30. So I get to my graph, and I'm going down, I'm waiting. And 30 should, here it comes. Okay. So just a little bit, probably right around between 27 and 28. So that's a long time to wait. Yeah, you get $30, that's a long time to wait. If you had thousands upon thousands upon thousands, that's a little different maybe. But again, whether I use 10, 100, 1,000, a million, I'm going to get the same answer any of those ways. So let's see if anything different's coming up here. You could either use this, or if you had an actual balance here, you could use that in its tripled value, which we're trying to use too. So let's see. 9, invest $1,200 in account paying 5%, come out of monthly, find the balance after 9 years. Alright, so 1,200. Compounded monthly, so be careful here. Make sure if you're not going to multiply 12 and 9 ahead of time that you have them in parentheses in your exponent, because otherwise you'll get something to the 12th power times 9. It'll be some ridiculous number. I'm hoping some of you are starting to look at these, and if nothing else, you're learning what answer is sensible and what's not. So anybody got a number they want to throw at me? Yes. Alright. And again, depending on if you went to the table or the other thing, it could be 21 cents, it could be 22 cents, because those had slightly rounding differences on them. But either one would work. If you got some ridiculously large answer, like 8,000 here or something, I hope you'd realize at this point that doesn't make much sense. And then finally, writing. We have to think. If given the option of 2 investments, describe how to tell which investment accrues more money. You can use graphical, examples, tables, function properties, whatever. Here's what I would try to do. When we had that problem on the e-worksheet that we did before, where I said he had the one deal compounding monthly versus the one deal compounding continuously, it's one of those things where you might want to actually draw up a comparison. So let's say you had something with 5% simple interest. Okay, let's say $1,000, 5% simple interest for 2 years. And then I compare it with $1,000, 5% continuously for 2 years, and see how much of a money difference there is. Now, you may find there's hardly anything. If you use a big number, like $1 million, you may find it's quite a bit different, just because of how much it's there. But this is your way of saying, I understand that this way makes a little more than this one, or something like that. Even if you were just to pop it into the calculator and say, well, if it was 100 years, it'd actually start making a difference. But now it's only 2 years, so it really doesn't make any difference at all. That's the type of thought process I want you to get into here. Okay. The question will be worded a little bit differently, so it'll direct you a little bit more tomorrow. But this is just to get you thinking about it a little bit. But this basically is the quiz. It's not going to be incredibly long. With the homework check, I wanted to make sure you had plenty of time for everything. We should be in pretty good shape. Then we can start logs on Wednesday.